Good morning, Earth Science, and welcome back to another day. Today we're going to jump into Chapter 10, which is on earthquakes. For those of you who haven't watched any of my videos before, feel free to pause them at any point in time as you guys get all the information down. You can go back and rewatch sections, take your time on it. We're going to be talking about earthquakes. They're a truly devastating kind of event that can occur. We talked about plate tectonics last chapter, and that's really important for this one. Earthquakes are caused by those movements in the plates, and we're going to jump into how that process actually occurs. But first, we need to define what is an earthquake. And more than 3 million earthquakes happen every year. About every 10 seconds, an earthquake happens somewhere globally. And an earthquake is the shaking of Earth's crust by a release of energy. So it can result in an erupting volcano, a collapse of a cavern. It can be the result of an impact from a meteor. If we get meteors that are big enough to strike Earth, they can cause an earthquake. The cavern is large enough underground, it can cause an earthquake. Most of the time it's going to be along something called a fault. And we're going to talk about a fault next. A fault is a break. Here it's this little black line in between these two in the lithosphere, along which movement occurs. So it's either up and down, side to side. Most of the time, these really large lithospheric plates have friction. As those two plates are sliding past each other, they're held in place by that friction. And this energy builds up as you have this one really heavy one trying to be pulled down by gravity, and this other one that's a little less dense, that's trying to pop up. It's trying to move side to side. When the force overcomes the friction and the plates suddenly jump, this is what causes that earthquake. This movement, this really quick movement, is what causes earthquakes to occur. Elastic rebound theory. This is after an earthquake happens, these plates are going to snap back together. So they're usually the same shape, but they've moved. It can be an inch, it can be several meters. It just depends on how much force was involved in that earthquake. So in this example here, in this timeline 1, you have this road together, and then it kind of stretches, and then snaps back to being flat again. And when it snaps back, it is now in a different position. Each earthquake has a focus, and each earthquake has an epicenter. They're a little bit different. The focus is the point at which movement first occurs. This is where the rock actually moves or the rock actually breaks, and is where the earthquake originates, and it's usually very far beneath the surface. The epicenter is if you move straight up from that focus. The epicenter is that first part where you actually reach the surface of Earth. That is the epicenter. So when we talk about the focus and the epicenter, they're just different spots inside of the Earth at the same area. The focus and depth. At divergent boundaries, they're really, really far down. They're 30 kilometers. At transform, where we have two coming together, there are these red dots and yellow dots here. They're really close to the surface. And then, the divergent was these green. And then subduction, these blue down here, are very, very deep, very, very far below the surface, up to 700 kilometers. The further down you move, the deeper you are inside of the Earth, the lower the amount of damage that you're going to get. Higher, closer to the Earth, more shallow, more damage. Deeper, less damage. Body waves. These are energy that's released from earthquakes, travels in waves. The same way as when you drop a rock into a pond and those waves kind of go out. This happens as well in earthquakes. They'll travel from the focus, and then they go through the material of the Earth, they go through the body of the Earth. And you have two different types. You have S and you have P waves. We're going to talk about, you can see on this little image here, there's these surface waves at the top. We're going to talk about surface waves as well. Sorry about that. P waves, they're known as compressional waves or primary waves. They squeeze and stretch the material as they pass through. Think of it like an earthworm. So you have this big stretched out material, and you have this convergent, where it's everything really close together, stretched out, compressed, stretched out again. And P waves can travel through solid rock, they can travel through air, magma, and ocean water. So they can travel through liquids, solids, gases, the whole works there. Let me readjust that for you. That's going to bug me. S waves are another body wave. They're also called shear or secondary waves. In this, these rocks are moving up and down. So this is like actually going like a wave. It moves at the right direction. So this wave is moving this way. These are making nice right angles to that wave. They can travel through solids, but not liquids or gases. So think of these as S waves. Think of them as solid waves, or shear or secondary, however you remember them. P and S waves do not travel at the same speed. It depends on the density of the materials around them, but waves move faster through things that are rigid and dense, that are closer together. And S waves move much slower. S waves are up here on this red. Move much slower than compressional waves. These guys are moving the same distance, but it's taking double the time for the S waves than it is for the P waves. So when these waves reach the surface, they no longer become body waves. These turn into surface waves. There's two types. There's love waves and there's Rayleigh waves. And these are waves, body waves that were body waves. They've reached the surface of the Earth and they now turn into surface waves. Love waves cause things to move from side to side. These are moving perpendicular again, but they're going sideways instead of up and down. Surface waves move much slower than P and S waves, and you can feel them very far from the epicenter. Remember, the epicenter is the surface. When we had that earthquake a couple years ago that was down in southeastern Idaho, we felt the love and Rayleigh waves as they reached us up here. They shook the ground a little bit. If you were around for that, you can remember it. Rayleigh waves, these travel even slower than Love's waves. So in order of fastest to slowest, it's P, then S, then Love, then Rayleigh. And they move in these elliptical patterns, or this kind of like this kind of way, like a clock almost. It's very similar to how you get ripples on the surface of water. And these are the ones that cause a lot of damage when we get to towns. Town buildings are not really good at moving in this kind of circular fashion. So to locate and measure earthquakes, we need what we call seismographs. These are used to detect and record waves produced by earthquakes. We then use this data from many different seismographs to locate earthquakes' epicenter and measure their magnitude, how strong they are. There's more than 10,000 seismographs worldwide. This is the global seismograph network here on the right. These stars are like the big stations. There are many, many smaller stations as well. These are only some of them. We have some down on Antarctica and in Greenland and on Iceland and all over Europe and Asia. Not a lot in Africa and South America, but a lot in North America and a couple in Canada. Seismographs need to measure different waves because each earthquake is potentially throwing off 4 different waves. So it needs 3 different ways to track them. One for up and down motion, one for things that are going side to side in a north to south direction, and one that are going side to side. And this is, I'm going to draw this kind of obliquely, in an east to west direction. So in these 3 different directions, they're tracking movement of the Earth's crust. And how it actually works is we have a seismogram. And a seismogram is this record sheet, this white paper, attached to a drum, usually inside of the bedrock. This drum is turned slowly by a clock so that it is always moving at a constant rate. There's going to be a pen that hangs down. It will move as this seismogram moves as well. It'll make a straight line until it senses some kind of movement in the Earth. When the bedrock moves, whatever type of wave it is calibrated for, up and down, north and south, east and west, it will move, and it will create these kind of squiggly lines that you see in like films and documentaries. So looking at a seismograph, we can tell a couple things. Remember that P waves are our fastest, so they show up first. P waves are going to be the first to show up. And then the S waves arrive, and they have this very different like up and down kind of pattern, almost sine wave. And then the greater the distance to the epicenter, the greater the gap here between this P and the S wave. If it's really close, these S waves might start, it might go P waves and then right into S waves. Or if they're really, really far away, it might go P, 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 and then S waves all the way out here. And then the surface waves are much bigger. They're moving the surface around, so thereafter they're slower. Remember, it's P waves, then S waves, then love waves, then Rayleigh waves. So to locate the epicenter, we can use different seismograph stations to tell us how far away the earthquake is. It doesn't tell us the location of the epicenter, it tells us how far away it is. So using 3 different stations, we can kind of triangulate. You can see on this one here, we had a longer P, and then the S waves are farther out, so we know it was further away, and we can draw this circle for how far away it could have been from C. And this one is a little medium length, so it's a medium circle, same thing, and then A is small, they came in very quickly, close together, so we could tell where that epicenter is there. So we'll use 3 different stations or more to use their distance to locate the epicenter of earthquakes. The magnitude of an earthquake is its strength, how strong it is. It measures the amount of energy released when these plates are slipping past each other. It was created by Charles F. Richter in 1935, our main scale for magnitude, and it's named after him. Each time you go up a number from a 1 to a 2, for example, this is a 31 times increase, and this number is important. It will be on your test. So each time you go up 31. So 1 to 3 is actually going to be 31 times 31, not 31 times 2, because each one's a 31 times increase for a much larger number. Richter scale is limited when we get up to the really big earthquakes. There's not enough difference between an 8 and a 9 to really be useful. Even though it's 31 times, there's a lot of range there. So we'll use something called moment magnitude, which is another scale that indicates the energy at the earthquake source. And this scale will be very different than those for the Richter scale, even of the same earthquake. So they're used mostly by geologists to kind of differentiate between an 8.67 and an 8.7 on a Richter scale. Earthquakes cause a lot of damage. They shake the ground. They cause foundation to fail. This process happens because these earthquakes release the sudden amount of energy. The waves move these buildings up and down, side to side. Most buildings can do the up and down, all right, the 90-degree up and down, but the side to side in that elliptical pattern in the Rayleigh wave, is very detrimental to them. During an earthquake, liquefaction can occur. This occurs when loose soil temporarily acts like a liquid. So if there's a building on this soil, it usually will become unstable and collapse. Solid rock is a lot less likely to liquefy than loose soil, so this is why we build houses on foundations. This car actually is a victim of liquefaction. This loose soil turned into a very liquid-like state and sucked this car into it like quicksand. And then when the earthquake was over, it re-solidified back into that loose soil, and now they have to dig their car out. Probably not great for the motor either. Aftershocks, these occur. These are smaller earthquakes originating close to the magnet of the large earthquake. They will start out strong. They'll be like an aftershock pretty quickly after the first earthquake, and then they'll get less and less likely. These are very dangerous though, because they can, even though they're of a weaker magnitude, that original earthquake might have damaged some buildings, and then these aftershocks will come in and actually break them and tear them down enough that they will fall. So they're very dangerous that way. Tsunamis are another risk we see in earthquakes. If we have an underwater earthquake or a landslide in the ocean, they cause these massive waves. This is a small tsunami here. It's throwing some cars. These guys travel very quickly. The deeper the water, the faster the tsunamis travel. And then when they get closer to the coast, they get bigger and they get slower. And they can cause a lot of damage. This guy here is causing a lot of damage. And there'll be a lot of insurance claims coming out this day. So to prevent earthquake damage, because we as a society don't like our buildings to fall down on us, um, we have building codes that are intended to prevent structural damage and collapse of earthquakes, of collapse of buildings during earthquakes. These are designed to save lives by preventing buildings from falling on people below. In this picture here, you have these kind of rubber shock absorbers under the ground, and this building is actually sunk into the ground to help it like bounce a little bit. It has these nice kind of bars that are crossed through here where they'll prevent that side-to-side motion. So they've got up and down and side-to-side protection, making this building a little bit more secure. The glass will usually be very shatter resistant, because we don't want shattered glass to fall onto people. That's a good way to get cuts and lacerations. Not a good time. 3 very powerful earthquakes happened in New Madrid, Missouri, of all places. Out here, it does not look like there's any boundaries. San Andreas is over here, and we can see that one very easily. Turns out there's a lot of faults buried beneath the sediment where these cracks or breaks in the lithosphere are. The reason that this is such a high risk area is because there's a lot of sediments and there's not a lot of preparedness. Unlike over here where we see earthquakes all the time, they're very prepared. New Madrid, Missouri was not. These happened in the late 1800s, early 1900s, so they didn't have any building codes or regulations at the time. So to predict earthquakes, we want to know 3 important things: where an earthquake will be, when it will be, and how strong it will be. Really, those are the 3 things that we're interested about when we talk about earthquakes. Is it going to be, in the United States? Is it going to be in Europe? When is it going to be? And then how strong is it going to be? So earthquakes are usually periodic events, meaning that they happen over a cycle. Using information from previous ones, we can hopefully detect future ones. By plotting the foci, which is the plural of focus, we can identify areas where the fault has not moved over a series of time, and this is called a seismic gap. And we think that these are areas where earthquakes could potentially happen, where this plate hasn't moved in a long time and it will. So this is a nice picture. We got the Alaska archipelago here, and you've got different dates of different earthquakes, and then you've got the Shumagon Gap right here, which is where we think the next big earthquake in the Alaska area will occur. So by studying Earth's interior, by using earthquakes, we can study Earth's interior. Most of what we know about the inner core, the outer core, the mantle, is because of the patterns of waves and how they travel through Earth. P and S waves speed increase when they go through dense material. They decrease through less dense. S waves can't travel through liquids. That's really important when we talk about our outer and inner core. And using this information, we can talk about some zones of the Earth and how these waves move through them, and kind of determine what the inside of the Earth looks like. Our first zone is the shadow zone. We're talking mostly about this one on the right over here. This is a wide belt on the opposite of the Earth from the earthquake's focus, and it's where a lot of the S waves don't come through. And why does this exist? And the reason for this is as the S waves travel through the mantle, parts of it are solid, parts of it are liquid. They can't pass through the liquid part of it, and they can't go into this outer core, which is liquid. So they get stopped here, and they go around the sides of it. The P waves also have a shadow zone, because as they go from a less dense to a denser material, they get bent more towards the middle here, and you get these little P shadow zones on the sides there. The Moho, which is this little tiny strip here at the bottom of the crust. This is an area in the Earth where the speed of the P and S waves changed dramatically. This was found by Andrija Mohorovic, sorry if I mispronounced that, in 1909. And he discovered this while he was looking at minor earthquakes. And this happens because the boundary, where this less dense rock of the crust, is met by the dense rock of the mantle, and these waves are speeding up as they're going into that denser mantle. And the Mohorovic discontinuity here. The transition zone, the mantle itself is not all the same density. The upper mantle kind of floats on this lower mantle. The lower mantle is more dense because there's more pressure on it. There's more material up here compressing it. It's more dense. It means that those P and S waves will travel faster through it. So the transition zone we found because these P and S waves speed up again. They speed up at the Moho, and they speed up when we get down to the lower mantle. I hope you learned a lot about earthquakes. I hope you learned a lot about Earth and its structure and process through this. If you have any questions, let me know. Have a great rest of your day, guys.